Hello everyone, and welcome back! In this video, we will be looking at a quick visual demonstration of column buckling in a two-story building. To start, let's put Euler's buckling formula up on the screen. Remember that this is the formula that determines the capacity of our column. As a structural engineer, our goal is to determine both the demand on a member and its capacity. If the capacity of the member exceeds the demand, then the design is adequate. If not, we need to change some parameters. Now, it's important to note at the start here that when analyzing compressive members such as columns, we need to broaden our perspective from a one-dimensional analysis to two-dimensional. So what do I mean by that? Well, let's first take a look at a member in tension. And let's recall what that failure mode looks like. And we're going to do that by pulling on this piece of electrical tape. So you can see as I pull on this, it starts to yield, and then eventually, if I continue pulling, it ruptures into two separate pieces. And just in case you missed that, I'm going to do it again, this time with a bit longer piece of tape. And again, as I pull on it, note that there isn't really anything much going on here aside from it elongating in the direction that I'm pulling on it. It starts to yield, and then it ruptures. So that wasn't really too exciting. There wasn't a whole lot going on with that piece of tape, as I said. It didn't pop out of plane, it didn't suddenly change direction, it just continued, everything was in one line. And this would be true of every piece of electrical tape that I pull on, or any material that I pull on. You would see the same failure happen again and again and again. So calculating the load capacity of a piece of tape in tension is very simple. It's just the cross-sectional area times the yield strength, and done. Now let's compare that to when I push down on some of these columns here with this model. So I'm going to apply compression to this first column here, and you can see the buckling shape that forms is sort of like an S. Now let's jump to this column here. Now note that it's the same overall length, it's the same material, this sort of springy metal. So theoretically, if this were the same type of analysis as in tension, we would see the same sort of shape occur. However, you can see we don't get that same S shape here. Instead, we get this C shape. So clearly there are some other factors at play here beyond just the material and its cross-sectional area. So hopefully you can see visually that compressive analysis is going to be a bit trickier than tensile failure analysis. There are more than just those two variables. Tensile failure, as I showed, always happens in line with the direction you're pulling. Compressive failure, however, depends on some other factors, and it can change. So what are those other factors? Well, again, let's look back at our formula. Pi squared, of course, is a constant, so that isn't going to be changing anything. Modulus of elasticity is a material property, so that only changes if we're swapping to a different material. So that leaves us with moment of inertia, the unsupported length, and this K factor. Now recall that the K factor is a term used to modify that unsupported length of the column, depending on its boundary conditions, or in other words, whether the top and bottom of the column are pinned or fixed. And note again that these three variables did not show up at all in our tensile analysis. When we measure the capacity of a member in tension, we didn't care at all about its moment of inertia, its length, or its boundary conditions. But let's get back to talking about columns. And let's first talk about the first changing variable, moment of inertia. Recall that in simple terms, moment of inertia is a geometric value that expresses a given shape's resistance to bending. So when I look at the cross-section of this piece of foam, I should notice that there are some axes that I can draw through the center of this shape that would yield larger moments of inertia or larger resistance to bending than others. In fact, the largest possible moment of inertia I could calculate would be about this axis. So bending about this axis here would generate the largest moment of inertia. And on the other hand, the smallest possible moment of inertia would be calculated about this axis. In other words, I've just identified the strong and the weak axis of this particular shape. Therefore, if I were given a scenario where the other two variables, that unsupported length and the k-factor, were the same in all directions around the column, it would be pretty easy to calculate the overall capacity of that column. I would just calculate the smaller moment of inertia, plug it into Euler's buckling equation, and done. That's my overall capacity. But if it's possible to have two different values in different directions for one variable, is it possible to do the same with the other two variables as well? Well, yes, it is. Let's take a look at this model again. Now, I'm going to start with these two exterior columns, and then we'll take a look at what's going on with that interior column. So again, as I push down on these two exterior columns, you can see that they buckle in this sort of S shape. So what is causing that to occur? Well, as you can see, these two columns have a beam framing into them along the front face of the building, and they both also have a beam framing into them along this short face of the building. So in other words, they are braced in this direction and in this direction. So their unsupported length is really only equal to one story. Now, let's compare that to the interior column here. As you can see, it does have beams framing into it in this direction along the long side of the building. However, if I turn it this way, hopefully you can see that there is no beam in this direction. So there is nothing bracing this column in and out in this direction. So the question is this brace here enough to cut the unsupported length of this column and increase its capacity like it did with these two? And of course, as we saw earlier, it does not. Now, note that the buckling here for this column, when I push down on it, does not and cannot occur in that shape this way, because it is braced by these beams here. And in fact, it would never buckle along this front plane. It's always going to buckle in this direction, right? Because in this direction, along the front face of the building, its unsupported length is just one story height, same as this column. However, in this direction, now its unsupported height is 2 stories, or in other words, it's been doubled. And if you pay particularly close attention to Euler's buckling formula, you'll know that when you double the unsupported length of a column, what you're really doing is cutting that capacity by 4 times, because that length is squared in the formula. So in other words, when we provide these two beams for this column, what we've done is we've improved the buckling capacity for this column in this direction. However, as I said, column analysis is a 2-dimensional game. So if you improve its capacity in one direction, you really haven't affected the overall capacity of that column at all. So this all leads us to the final question. If we can have different values for the same variable about 2 different axes, is it possible to create a scenario where we don't know for certain which axis will fail first? Well, let's look at this column again. It buckles in this direction, right? It buckles into the long side of the building. Now, it's doing that, of course, because its unsupported length is double what its unsupported length is in this direction. But what if we were to provide a rectangular column here instead of this round circular column? And what if we were to orient it such that its strong axis is into and out of your screen? In other words, the strong axis bending is oriented in this longer unsupported length direction. Well, now we have created a scenario where we have a weak axis with a small moment of inertia, but a shorter unsupported length, and we have a strong axis with a large moment of inertia, but also a larger unsupported length. So which way would that column buckle? Well, in that scenario, we would need to run the numbers about both axes. The small number, of course, would be the controlling value that determines the overall strength of the column. So remember, column analysis is a two-dimensional game. Pay attention to both primary axes, and always choose the smaller number when determining capacity. Also, be careful when you remove sections of floor near a column. You may think that by removing floor area near a column, you are removing load from that column and therefore removing demand and making that column's life easier. But you may also be removing bracing for that column and significantly increasing its unsupported length and therefore decreasing its capacity, which would obviously make the life of that column much more difficult. So hopefully this visual demonstration of column failure buckling gives you a clearer picture in your mind of how columns fail, so that you can use the Euler's buckling formula more effectively.